You'll know you'll see. You'll see. Kyle, you're taping?
Yeah, you're live. Welcome to the whiteboard.
How's my hair?
Looks good.
Pretty good.
Looks good.
Okay.
We're ready.
All right, kids. So question number one was about power. Lots and lots of concepts and stuff to integrate regarding power. I put up the 12 steps the other day. Those are in the textbook. Those should be in your notes. But the question is this. And so this is just going to be an abbreviated version, just to get sort of to the answers. mu1 is greater than mu2. mu1 corresponds to the speed of red cars, and mu2 corresponds to the speed of cars in general. The hypothesis is that red car owners, at least when I was younger, there was this myth that the insurance companies charged you more. I have no idea if it's true.
I think it's still
If
true.
you have a red car, because red car owners drive more quickly.
It's because they like stand out, so they get caught more.
That could be. Okay. So with that said, you're given the population mean for the general population at 70, and you're given that population mean for red car owners, the special population, is 80. You are given also that n equals 25. You're given also that alpha equals 0.01. Okay, so this is all the given information that you need. So here's the comparison distribution. Comparison distribution is a distribution of means. I try to make it a little bit squishy. The mean for the comparison distribution is the mean for the general population, which is 70. The standard deviation for the comparison distribution will be represented by sigma sub m sub 2. And again, this is all being videotaped, and Kyle will dutifully put this up and send this around. Okay, sigma sub m sub 2. Population standard deviation is 7. So sigma 2 equals 7. To get sigma sub m sub 2, we have a two-step process. A, we have to get sigma square sub m sub 2, which is sigma square over n, which is 49 over 25. Which is 1.96. And then sigma sub m sub 2 is the square root of sigma square sub m sub 2, the square root of 1.96. I have that as 1.4. Which is what I got here. So the standard deviation of the comparison distribution is 1.4. Some people put the population standard deviation. You remember, once your n is greater than 1, you're dealing with a distribution of means. Your standard deviation must be a standard deviation of a distribution of means. Now, I'm going to, this might be slightly different order than in the 12 steps, but this upper distribution, u sub m sub 1, has a mean of 80. It therefore is to the right of the lower distribution. It is to the right because this x-axis means the same for both distributions, and 80 is greater than this 7. So that's why that is to the right. We're going to get z critical. Z critical with a one-tailed z-test, or one-tailed z-test, with point alpha 0.01, or 1%, you're going to look in the table. I happen to have this memorized, but you're going to look in the table, and what you're going to find is that particular z critical equals 2.33. 2.33 is the particular z that has 49% of the distribution between that particular z and the mean. So this is something we've done a whole bunch of. You're gonna go to that very first table, and z critical is 2.33. One thing about the power examples, if you get any of these things wrong, you're gonna get the answer wrong. So there are different points where there's possibilities for error. We're next gonna get what I'm calling M critical. What is that score as a raw score? M critical equals Z critical times sigma sub M sub 2 plus mu sub M sub 2, which is 1.4 times 2.33 plus 70, which is 73.62. Okay, 73.62. That means that to reject the null hypothesis, if you were going to carry out the hypothesis test, oh, did I get that wrong? Is that? Oh yeah, 260. Right. Thank you. White points right there. Okay, 73.26. If you were going to carry out the hypothesis test, your sample mean from the special population would have to be greater, and that's a critical point, greater than a raw score of 73.26. Take a look on that upper distribution. If this is 80, where's 73.26? Way over here. So that becomes M upper. The standard deviation is going to be the same, sigma sub M sub 1 equals 1.4. And now, we're going to convert that to Z upper. Z upper equals M upper minus mu sub M sub 1, the mean of the distribution that we're talking about, divided by sigma sub M sub 1, which equals 73.26 minus 80, so it'll be a negative number, divided by 1.4. Which is negative 6.74 divided by 1.4, which I have negative 4.81. So as a z-score on the upper distribution, that is a z of negative 4.81. If you look at the table on page 325, you will find that once your z, in an absolute value sense, gets greater than 4, the percent between mean and z is always going to be 50%. In other words, a z-score of 4 is so extreme that you can almost guarantee that 50% of the scores are here, because it's so unlikely to come out of a normal distribution. We know that 50% of the scores are here. What percentage of the scores are more extreme, overlapping with alpha, in that upper distribution? Everything greater than 73.26 is 100%. 50 plus 50. All of it. Some people, and it's really important, you have to really understand the concepts to know it's to the right. So you gotta think about it. We're predicting that the special population is greater than, so that means that we're gonna be focusing on stuff that's greater than that critical value. So power equals 100%. Okay, this is videotaped, so you can go back and watch it slowly and carefully. But I'm pretty sure that that's all the information. Question number 2 is beta. Beta is essentially a probability of type 2 error how likely are you to fail to reject the null hypothesis? Well, if I'm 100% likely to reject the null hypothesis, then the odds of me failing to reject the null hypothesis is completely zero. 100 minus 100 is zero. There's no way I'm going to fail to reject the null hypothesis. So that is question number 2. Beta equals 0. It is just the complement of power. Question number 3. Effect size. You had to compute several effect sizes during this exam. Effect size in a power example equals the absolute value. By the way, if you put a negative sign, I typically didn't care, but it's the absolute value of use of 1 minus use of 2 divided by sigma. I can put sigma, I can put sigma 1, I can put sigma 2, those are all the same as the population standard deviation. That is going to be 70 minus 80 over 7. Which is 10 divided by 7, which is 1.43. Effect size indices are always in terms of population information and never in terms of distribution of means information. That's how it differs from statistical significance computation. So the effect size here is 1.4. You're next asked how big of an effect size that is. 0.8 is considered large. 1.43 is bigger than that, so this is definitely large at the very least, so sort of very large. Okay, I'm not going to pause for questions in the name of efficiency, but again, I'm just making sure that I'm comprehensive. If someone says, wait a minute, you missed a step or got something wrong, do correct me, but otherwise we're just going to try and put you through this. Question number so this is question number 4. The effect size is 1.4. Question number 5 is a multiple choice question, conceptual, about type 1 versus type 2 error. There is no type 3 error. The unfundamental attribution error is something that I totally made up. Type 1 error is when you find something but you're wrong, there's not really anything there. Type 2 error is when you fail to find something, but you should have found something. In this case, Professor Schmedley tried to demonstrate that, I think, owning dogs led to positive mental health outcomes. In his research, he failed to find significant effect, and then he was never heard from again. And it turned out that his students on 20 different occasions replicated his studies and found out that in every single one of those studies, it turns out his research hypothesis was correct, suggesting most likely that his research hypothesis is correct. But he failed to support the research hypothesis. That is simply the definition of type 2 error.
Is that a real name?
Schmedley?
Yeah.
Possible. Question number 6. Okay, so now there were 3 t-tests. Question number 6 is a one sample t-test. Okay, you want to see, I think I initially, when I first wrote this in 1996, I wrote beers, and at a later point I decided it'd be smart to change it to sodas, and I think I only changed it in one spot, or not the other. I can't imagine that having an effect on the math, but I thought it was funny. I'm going to stick with sodas. It doesn't really matter. If you know that the average number of sodas per month that New Paltz students drink is 3, so use of 2 equals 3. you do not have the population standard deviation. And you want to see if people in your dorm drink more sodas than the university on average. So the research hypothesis is that the use of one special population kids in your dorm is greater than use of two. That's the research hypothesis. I'm assuming, like, if you're gonna do a redo on this, flesh things out, write out your work carefully. I'm doing this efficiently just to get the basic understanding on video. If I were gonna redo this, I would put the null hypothesis too, and so forth. We do not have, so here's our comparison distribution. It's a T distribution. Use of M sub 2 equals 3. We don't have sigma sub M sub 2, so we're gonna have to get S sub M sub 2. S sub M sub 2 is an estimate of sigma sub M sub 2. So we're gonna need to get that through the numbers. Here's a number we have from the students in your dorm. Mean is 4. Okay, so this is just the process for computing S sub M sub 2 because that's needed for the comparison distribution. That's going to do X minus M. This is the deviation score, which is 3, negative 4.
But it's -1.
Thank you. Thank you. I love that, by the way. Just like 3, negative 1, and negative 2. It wasn't going to add up, so I think I would have had to have come to that. Thank you for that. Okay, so deviation scores are 3 and negative 1 and negative 2. Next, we're going to square these. We're doing this all from a practical standpoint to get S sub M sub 2. So this is 9, 1, and 4. Sigma X minus M square is 14. S square equals sigma X minus M square divided by N minus 1, which is 14 divided by 2, which is 7. S, I'm going to put S, I'm going to make a big point out of this. We're not going to use S for the t-test calculations, but as I've said before, S is conceptually really, really important. S is the square root of S squared. Which is 2.65. I'm going to put a box around that and just kind of put a pin in it for now. We'll get back to it. S squared sub M sub 2 equals S squared divided by N, which is 7 divided by 3, which is 2.33. And then S sub M sub 2, which is what is needed for the comparison distribution and for the t-test, is the square root of S squared sub M sub 2. Is 1.53. Okay, we're just about done with this one. Alpha equals 0.01. So this is 1% here. The degrees of freedom equals 2. And it is a one-tailed test, because we predict more that students in your dorm are drinking a little too much soda. So I'm going to go to my table, okay, which I'm going to give you again, always on the exam. Go to my table. And the example I gave you, actually what I use in my textbook, I based identically on the tables that I'm giving you for the exams. It's a one-tailed test, 2 degrees of freedom, alpha equals 0.01. So the only number there is 6.965. Kyle, for the camera. So that's what you do. You figure out the number of tails, you figure out the degrees of freedom, you figure out the alpha. There's a single number that's going to emerge. This is 6.97 round. So T critical equals 6.97. So to reject the null hypothesis, our obtained T is going to have to be greater than 6.97. Probably not going to happen. That's a pretty far end zone like that. T obtained equals m sub 1 minus mu sub 2 divided by sigma sub s sub m sub 2, which equals 4 minus 3 over 1.53. Which is 0.65. So that is T obtained. T obtained is here. Is T obtained in the alpha region? Simply not. We failed to reject the null hypothesis. We have not provided evidence showing that students in my dorm drink more sodas than students on average. That actually is questions 6, 7, 8, and 9 right there. I know I wrote question number 6 just because I was thinking in order. But actually, question number 6 is a standalone, and I think it's really important. Question number 6 is essentially this. What is S? Now, I didn't word it exactly that way, but in class I defined S compared to all the different indices of variability. S has a really important meaning because S is their best estimate of sigma. It's our best estimate of the population level standard deviation. I do know that S sub m has calculation meaning. From a calculation standpoint, S sub m is important because it's used for computing T, but conceptually it's not really very meaningful. Conceptually, what's meaningful, if you're going to describe to someone what's the average amount of the scores varying in the population for that variable, you would, if you had sigma, you would give them sigma. You don't have sigma, you would give them S. So in S, and this is wording that was used exactly in class and exactly in the textbook, what is the best or unbiased estimate of the population standard deviation? The answer simply is that's S. S is your estimate of sigma. And the answer is 2.65. Remember I put a box around it because I said we're going to come back to it. So S equals 2.65. Again, for calculating the t-test, not necessary. For describing the concepts to someone and understanding the meaning of all these variance estimates that are used in t-test, it's more important. Okay, we're getting up to the South Park again, just to show you how data. Do they still make these South Parks? Is it still really funny? Pull up something like okay, I rescind the question. When that thing came out, though, it was almost like when The Simpsons came out. It was such a game changer with the TV show. Not always played. Okay. This is a really important question, and I tried to sort of give a hint. You remember I said here's a hint during the exam? There's a very big difference between our predictions and our actual data. And this question was designed to tap an understanding of that concept. Sometimes our predictions are completely wrong. That's an important and humbling lesson of the scientific process, which is why I included this question this way. But I also, since I know that's a little abstract, that's also why I kind of gave people a little hint during the exam. So we have scores before, these are happiness scores. So the prediction is that watching South Park makes people happier. These are happiness scores before watching South Park and after. This, by the way, is a within groups t-test. We have two variables for the same participants. So we're looking at variability within one group. That's why it's called a within group t-test. D-bar predicted, before we even touch pen to paper, D-bar predicted, if you're predicting that South Park makes people happier, it's a one direction, right? It's a one-tailed t-test. And we're predicting, before I even put numbers up here, that these numbers are higher than these numbers. The prediction is that the scores will increase. In other words, if it makes people happy, I might be like a 1 on a 1 to 10 scale. I'm mopey today, and then, oh my God, I just watched that funny episode with Stan, where it's Christmas. Anyways, and then, well, I'm happy now. So the prediction is that it makes you happy. The prediction is these numbers are higher. If that's true, then D bar cap, our predicted average difference, is going to be negative. Because 1 minus 10 is negative 9. So the prediction is that the differences are negative. Now, not only is that sometimes a little complicated for students to wrap their brains around, short version is, and I'll put this on the video, if you're predicting these numbers to be higher than these numbers, D bar cap will be negative. If you are predicting these numbers, the post numbers, to be lower than the pre numbers, then D bar cap is predicted to be positive. Because 10 minus 1 would be 9, or 1 minus 10 is negative. So look at that setup. We're clearly predicting these numbers to be higher. We're predicting the differences to be negative. The research hypothesis is that D bar cap is negative, or less than 2. We will come to find that we're totally wrong. So the scores are 10, 9, 5, 8, and 8. The post scores are 2, 2, 8, 3, and 2. These scores are yoked with each other. They're from the same participants. This is a within groups t-test. A few people did the between groups t-test process, which was the incorrect process. You give the mood scale to 5 individual people before and after. So it's the same participants. So now we're going to get the differences, which is 8, 7, negative 3, 5, and 6. Okay, so we can see here that with one exception, these are positive. Right out of the gate, it's like, wait a minute, we were totally wrong. You could even look at the raw score numbers and say, wait a minute, my prediction was wrong. People were very happy at time 1, except for this one dude. Everyone else seemed less happy at time 2, right? So that's meaningful information. Our prediction was the opposite of the actual data. D bar, or the average difference, is 4.6. D minus D bar. Okay, so this is the same process. We're gonna ultimately get another t distribution, by the way. This t distribution will have degrees of freedom of 4. Alpha equals 0.05. So just setting things up a bit. And when we look up, I'm just gonna do this and then hop back over here, just to set up the end zones for the comparison distribution. When we look up 4 degrees of freedom, alpha of 0.05, one-tailed test, we get 2.13. But remember, the sign of t critical follows the research hypothesis. Therefore, it's not 2.13, rather it's what? It's negative 2.13. It's over here. So this is a really interesting scenario. Getting that correct is critical for the whole problem. Putting it on the correct side is critical for the whole problem. Okay? So now we're going to go back to that. That's t critical. Now we're going to work toward t obtained. D minus d bar is, so I'm going to refer to Madeline's words, which is more better presented, I think. Okay, so here we got 3.4, 2.4, negative 7.6, 0.4, and 1.4. That simply is each difference, subtracting out the average of the differences. D minus d bar square is 11.56. 5.76, 57.76, 0.16, and 1.96. Okay, are we good? Okay. So next we're going to get sigma d minus d bar square, the sum of that column. Which is 11.56 plus 5.76 plus 57.76 plus 0.16 plus 1.96, which equals 77.2. Anyone else get that? Okay. S square equals sigma d minus d bar squared divided by n minus 1, which is 77.2 divided by 4. N is 5, and it within groups t-test like this, so that divided by 4 equals 19.3. So S squared is 19.3. I'm going to compute S at this point. Remember, this is a sidebar, but it might come back later for the effect size. S equals 4.39. Put it on the side and put a box around it. You may need to come back to it, and it has independent conceptual meaning. S squared sub m equals S squared divided by n, which is 19.3 divided by 5, which is 3.86. And S sub m, so d bar equals 0. There's different ways to represent this on a within groups t-test. Usually I'll put d bar equals 0 for the comparison distribution. S sub m equals the square root of S squared sub m, which is 3.86 square root, which is 1.96. T obtained equals d bar over S sub m, which equals 4.6 divided by 1.96 Now, here's the thing, and this is an important integration of all the concepts. 4.6 divided by 1.96 equals 2.35. On this distribution, if 0's here and negative 2.13 is here, then 2.35 is going to be to the left or to the right of the mean. It's a positive number, it's way to the right. T obtained equals 2.35. Is that in the rejection region? It's not. Now, this is a weird thing. If it were negative, if they had the same sign as each other, it would be. But this is one where it's like you were proven like totally wrong. So that's a really important nuance. And this is the distinction between predicted data and actual data. So that was designed to be kind of a lesson on that particular topic. You failed to reject a null hypothesis. Cohen's D equals D bar over S. You remember Cohen's D always is based on population level information, not distribution of mean-based information, which kind of means it's independent of sample size. So that is 4.6 divided by 4.39, which equals 1.05. So it's actually a large effect size. It just happens to be a large effect size that's totally inconsistent with your hypothesis. So that brings us to question 30. Okay, final one. The between groups t-test. Also, a one-tailed test. Use of one is soccer players. Use of two is rugby players. These are now two different populations, or they were drawn from two different populations. The research hypothesis is that the soccer players eat less pizza than do the rugby players, because those rugby players are wild animals. I played for 1 month of my life and broke a finger very quickly, so I don't recommend it. And so this is just the opposite. Now, someone asked me, what if I want to set it up the other way with the other one having a subscript of 1 or 2? If you switch it, you're conceptually and like legally allowed to do that, but realize that if you do that, make sure that everything that you do related to that is consistent with that change that you've done. Otherwise, it's not going to work out. Okay. So now, so you have x of 1 as your soccer players, 12, 0, and 0. X of 2 is going to be your rugby players, 6, 10, and 8. This is the number of slices of pizza eaten. This one dude's a pig. Okay, so now, remember our comparison distribution is going to be a distribution of distribution of differences between means. Which is going to have a t of 0 and a standard deviation that is s sub diff. So we're going to need to figure out s sub diff. That's the really important part of this process. Before that, let's get our t critical. We are predicting that mu sub 2 is greater than mu sub 1. And because of that, we're predicting ultimately t obtained is going to be m1 minus m2 divided by s sub diff. So given our situation, we're predicting negative. We're predicting t obtained to be negative because we're predicting these numbers to, on average, be lower than these numbers. So if the mean of this is lower than this, then t obtained is negative, and the sign of t critical follows your research hypothesis. So if your research hypothesis is predicting that the t will be negative, then your t critical is going to be here. So here's t critical. Now it's based on total degrees of freedom, which is degrees of freedom 1, which is n1 minus 1, which is 2. So df1 equals 2. So it's 3 minus 1 is 2. And df2 also equals 2. Because 3, there's 3 here, 3 minus 1 is 2. And df total equals df1 plus df2, which equals 4. We're told alpha is 0.05. This is also a one-tailed test, so I'm going to look in the book, and I'm going to see that t critical equals 2.13. In this case, negative 2.13. Again, we have to put the negative sign there. There's a single number, so when you look at 4 degrees of freedom, one-tailed test, alpha 0.05, 2.13 is what shows up. So you really need to get familiar and used to that part of the process. So this is alpha over here. Now to figure this out, we have to figure out a whole bunch of other things to get to S sub diff, but we will do that. So I'll walk you right through that process right now. M1, 12 divided by 3 is 4. X1 minus M1 is 8, negative 4, negative 4. X1 minus M1 squared, 64, 16, 16. So sigma X1 minus M1 squared is 64 plus 32, which is 96. S squared is 1 equals 96 over n1 minus 1 equals 96 divided by 2 equals 48. So S squared sub 1 is one of the pieces we need. It equals 48. Now we're going to get S squared sub 2. The average here is 8. X1 minus X2 minus M2 is negative 2, positive 2, and 0. We're now going to square those. X2 minus M2 square is 4, 4, and 0. Sigma X2 minus M2 square equals 8. S square sub 2 equals sum of the square deviation scores for variable 2, which is 8, divided by the degrees of freedom for the second sample, which is 3 minus 1, which is 2. So it's 8 over 2, which equals 4. S square pooled equals df1 over df total times S square 1 plus df2 over df total times S square sub 2. So this is 2 divided by 4, 50%, 0.5. This is 2 divided by 4, which is 0.5. So it's essentially going to be the average of these in this particular case. So that's 52 divided by 2, which is 26. So S square pooled, another critical piece of the puzzle, is 26. S square pooled is used for both S square m sub 1 and S square m sub 2. S square m sub 1 equals S square pooled divided by n1, which is 26 divided by 3, which is 8.67. S square m sub 2 equals S square pooled divided by n sub 2, which is also 26 divided by 3. Since the n's are the same, it's acting the same for both of these. So that is also 8.67. S square sub diff simply is S square m1 plus S square m2, which is 8.67 plus 8.67, which is 17.34. And S sub diff, holy grail in this case, is the square root of S square sub diff, which equals 4.16. So the standard deviation of our comparison distribution is 4.16. T obtained equals mean 1 minus mean 2 divided by the standard deviation of our comparison distribution. That equals 4 minus 8, which is negative 4, divided by 4.16. Which is negative 0.96. Is that T obtained in our rejection region? It's not. It's not in that defined region more extreme than T critical. So therefore, we are going to fail to reject the null hypothesis. There's one final question, which is, what is the effect size? So with a between groups t-test, Cohen's d equals m1 minus m2 divided by S pooled. Remember, S pooled, we put it, I think we put it somewhere. Well, maybe we didn't yet. So S pooled simply is the square root of S square pooled, which is the square root of 26, which is 5.10. So this is 4 minus 8 divided by 5.10, which is 0.78. So that is the answer to question number 17, 0.78. And question number 18, very simply, says in terms of Cohen's convention for effect size, I accepted 2 answers on this. This is, 0.78 is very close to 0.8. Personally, I would have put large. Some people put medium because it didn't quite achieve large. I was fine with that and accepted both of those. So that is all the work for the 3rd exam. If you're interested in doing test corrections, it will help you understand this stuff better, which is a major, major goal of mine. To be honest, it's like my life's purpose, as dramatic as that might sound. And I really hope people take me up on that. Again, if you are going to do that, please do follow the process. Kyle, you can end the video now. Thank you.